Welcome everyone to our February DSUG meeting. I just wanted to say that Matt, Yana, and myself, as we've been working on trying to put together content per month, we've been trying to mix it up so that some months have like we had recently talked about ethics in data science and kind of the policy issues and all of these things. And today we're jumping back to another area, which is just straight data science and gaining some really interesting insights from new things that are happening within the field. And so we have two presentations today. First will be Anton, and second will be Matt, our very own Matt. And so I'll just quickly read a little bit about Anton before he begins his presentation. I'm sure some of you have already read this at the meetup site, but Anton Antonov is at Sendo Data LLC. He's a senior research scientist. He used to live in Champaign-Urbana, just as he mentioned, but he is an applied mathematician with 28 plus years of experience in data science. I mean, there's so much that he's worked on, but in the last 12 years, he's focused on developing machine learning algorithms and workflows for different industries. So music, movies, points of interest, recruiting, and healthcare. And now he's working on operations research and data science applications to manufacturing and healthcare. And just as a tidbit of knowledge, he used to be at Mathematica. That's why he was right here in Champaign for some time. But today's presentation, which just looks super cool, is entitled Anomalies, Breaks, and Outlier Detection in Time Series. So without any further ado, I will hand it off to Anton. Thanks so much, Anton.
Thank you for the introduction, John. And since Joseph, I think your name is Joseph, right? Pronounce it correctly.
Yes.
He introduced, he said this is going to be straight data science. Actually, it's going to be very convoluted data science. This is an example, maybe I should have given it later on, but this is an example of time series from the National Renewable Energy Laboratory. And so we're going to be discussing algorithms for detecting anomalies. I'm going to use this mind map here. So the mind map, it's a little bit more ambitious than what I probably have time to do in the next 25 minutes. But I would like to mention that I want to flavor this presentation with this several topics. So I program both in Mathematica and R. Mathematica and R are very close languages. If you compare them to anything else, they're also quite different. Now, this material I'm showing here in the algorithms is new, but I gave a similar presentation 16, 17 months ago at the Wolfram Technology Conference in 2019, titled exactly the same. So I'm going to be using Quantile Regression. That's not required to do anomaly detection, but Quantile Regression, the modern version of it, theoretically and computationally, was developed by Roger Kionka. He was a professor at University of Illinois Urbana-Champaign. He was both professor in physics and statistics. He's professor in England right now. Software monads, I'm going to be using software monads. If that name scares you, you probably used it in one way or the other when you do pipelines in R. Why I'm mentioning software monads and how they relate to University of Illinois Urbana-Champaign. In object-oriented programming, there is an important contribution which started. One of the contributors was from the University of Illinois Urbana-Champaign. It is called design patterns. So software, I use the software monads, the monadic pipelines. I use them as a certain type of design pattern, and obviously it is the way it is used, say, in R. I'm going also to do some flavoring with COVID-19 data. Maybe we'll have time to discuss large collections in time series. That would be nice. I'm not particularly sure how far we can go with it. So the basics which you see here, basic simple algorithms and quantile regression algorithms, I do have measuring success. I have interactive examples for those. And but before doing the interactive examples, like just more formally, like let's kind of introduce the subject matter. So I'm going to mock a question and answer session. So I mean, it's an interesting question, right? What exactly are anomalies? And some of the examples I gave here, like initially, let me bring this up. This example, as I mentioned, this is energy consumption data from the National Renewable Energy Laboratory. So you can see the different, the time series represent energy consumption. Like you can see how, for example, the cooling inversely correlates with the heating, right? So you can see when the heating is on, this is here, the cooling is not on. And these parts you see here, they're seasonal, meaning during the weekends, we have these dips which go down, and during the weekday, you have these parts here in the time series. So what kind of anomalies do we see here? So obviously some anomaly, something like this here, the tip of this time series. It's like anomaly overall. It might be anomaly throughout the whole time series, but also it's an interesting question. Is any of these points, are they contextual anomalies? Are they anomalies if you just look, say, locally into this time series? Now here we see a typical structural break, meaning if I fit some curve, or if I fit, say, 3 curves, I'm going to have one here, one here, one here, and then another one here. 3 lines, piecewise linear function, all of the slopes are going to be very different. So this is structural break. The structural breaks were kind of defined through the modeling. So I mentioned contextual anomalies, point anomalies. I do actually have another time series data to show. Another example of this is the so-called Numenta benchmark. Numenta is a company that it does different kind of algorithms for time series detection. I think they work with brain imagery and stuff like that. So you can see in their benchmark, they have shown in this time series different type of anomalies, and they expect anomaly detection algorithms who made to perform or to detect over this benchmark to detect these anomalies. So all right, so these are the examples. I'm going to go back to this is like definitions, and here, what is the best anomaly detection algorithm? And there's not best one. Every algorithm for anomaly detection is good in some, maybe relatively not necessarily narrow, but in some cases they're more universal, some cases they're more specialized. There are many people who do, in many packages and implementations of different anomaly detection algorithms for time series. So can we forecast anomalies? So this is what I'm discussing right now. We're detecting the anomalies. We're not forecasting the anomalies. If I go back to this example here, I'm not trying to see how this time series is going to extend further in the future, and do I get some anomaly which is being listed here. I assume I have seen the whole of the series, and then I'm detecting an anomaly in it. And so the most interesting message, I don't know, I thought it was interesting. Basically, I have conversational agents which generate code for doing not just anomaly detection, but any kind of regression workflows. I thought I'll start with them, show them at some point, but I guess we'll see, maybe at the end of the presentation. The most important message is, I would say, you can make your own anomaly detection algorithm. You just make it and you test it. And in order to test it, you need to do certain amount of scaffolding. You need to use some test series, like say something like the tests I'm mentioning here. And then you try to see how your algorithm performs. We're going to, the simplest algorithms in this, I would say, I'm going to show it, in my opinion, the simplest algorithm, which actually produces some non-trivial and good results is to partition the time series into overlapping parts and use a anomaly detection, like from a unsupervised point of view. This is going to be my first example, which I'm going to show. The presentation can be found at GitHub. You can, I have put the materials here. This is an R project. You can download it. You can see some of the notebooks. This notebook we're discussing right now, it's being listed here. All right. So it's a very interesting question. What happens if we have collections of time series, and how we define anomalies in those situations, and how we what kind of anomaly detection algorithms we can do there. Maybe I'm going to, since I said I'm going to do some flavoring with COVID-19 data, I'm going to show something here. So this is the Apple mobility trends data, which is from the Apple site. So should have some link here. If we go, yeah, you can get the data from here. So Apple have taken data from before COVID, normalized it at 100%. This data is request to Apple Maps. So again, we can see some seasonality here. If I make some, just to be more clear. So here we kind of see how I didn't mark the weekends here, but basically the dips you see here, they become during the weekends. When we have this higher when people look for Apple Maps, this is usually around, say, Friday and Saturday. And there's also some seasonal, we can see the COVID-19 lockdown policies were reflected in this request from the maps. And there's some, also there's some kind of seasonality here, like global one, which is related to the seasons. Let's actually use this example from Nice, France, right? So French, they tend to go on vacation in July and August, and that's why you see this kind of high up thing. And you can see these 3 weeks here, they're very prominently shown. So Apple data, we have driving, we have walking, and transportation. So this kind of data is being used. If we want to see some more of this analysis, you can go to and this is probably what I was talking about, seasonalities. So if I zoom this, or whatever, I'm not going to zoom, but here say the weekends are being marked. The Sundays are marked with these orange lines. So how exactly, what exactly is the analysis on this data, how it is being transformed, and some other things given here. So back to this one. So with, so here the anomaly, if we can, there's obviously some kind of anomaly which is contextual. But there's also this, let's actually claim this to be an anomaly, right? So can we actually find out that this part here is anomalous given the whole time series? So these are the type of questions I'm going to be interested in. I have 3 panels. I should have said this in the beginning. My presentation is in this middle panel, right? This panel here is for the interactive examples. And I have one more, which is for examples with Mathematica, which only structural breaks I'm going to discuss with Mathematica. So one of the things, or one of the missions I have with this project in machine learning is I do want to replace expertise with enthusiasm. So it's in some sense, this in machine learning, in mathematics, we try to automate as much as possible different algorithms. One of the easiest things to automate with machine learning is machine learning workflows. And many of these workflows I'm showing, I have been doing different types of automations with conversational agents, with algorithmically just through the signatures of the functions, and etc. So as I mentioned, I do want to discuss how quantile regression is being applied to this, and maybe I'm going to be using too much quantile regression here. That's not. I want to repeat this. That's not necessary. you can do anomaly detection with other algorithms. So before showing the first example, I would like to mention that this is a basic type of, in all of the algorithms we're going to be discussing, we assume that we have one-dimensional outlier identifiers. So you can see 3 of these outlier identifiers here: Champaign, Quantile, and S+. So they're relatively easy to define. Champaign is the most permissive one. The Quantile identifier is less permissive, and then we have the S+ one. All right, so here I'm going to get the example. Oh, this needs to wake up. So this is the, so we're, the rest 10 minutes, I'm going to be doing some interactive examples. So this is a financial time series. And so I think it's General Electric. So I mean, we can see some of these points considered anomalous. I mean, we might agree that they're anomalous, but what is exactly happening here? I'm taking these points, right, like sequence of points, and I partition them into overlapping windows or blocks of 10. So this is what you see here. This heat map shows this kind of partitioning. So I'm basically taking these overlapping windows. And now I apply a nearest neighbors, geometric nearest neighbors algorithm to them, and I try to see which of these points, they are multidimensional points in 10-dimensional space right now, which of them is has fewer neighbors, fewer than the average amount of neighbors. So if I change this to say, you know, say 5 overlapping, so we can see what they're like changed. This the dimension here changed. We now have a somewhat different picture. You know, we found more outliers. I can, if I go further with this, the outliers are going to be kind of smoothed out. Now what we see here, they're more like variance outliers. So they're not so much like this individual point outliers, but they're more like of larger blocks, which makes sense because I'm changing the window size. Obviously, I can also take into account how many nearest neighbors I'm considering. This was detrimental. And so let's actually go back to, so using different identifiers, using outlier identifiers, like using different neighbors, I'll be producing slightly different results. It's a very interesting question. Okay, well, then, especially after making this big statement that I want to replace expertise with enthusiasm, how do we actually select these parameters? So this one, this is the most important message I mentioned. It's going to be in that direction. All right, so this here, if I go back to my presentation and the interactive examples, this is the first one. If I go to the mind map, in the mind map, that was, this is the simple algorithms. If you find the mind map on GitHub, you can, this is a link to the interactive interface. The next I'm going to discuss is how to do quantile regression based algorithms for anomaly detection. Actually, that's, I do have an interactive example in Shiny apps, but I'm going to use one on my local machine, which actually uses a time series from Nice. So here, and I promised I'm going to put the interactive examples in this third panel. So let me move it here. So let's go back to this example here. So what I was showing here, this is for Nice, France, right? So I am going to make 2 in order to kind of to be more clear what is the resemblance with this interface here. So let me resize it, I guess, right? So let me put data axis and joint plot. So yeah, and this is basically, you can see here, this is the data which I have for this time series. Now, quantile regression, this is the lines you see here. They're specified through probabilities 10%, 50%, and 90%. So if I make this point plot, what I claim to have done with the quantile regression is that each of these curves separates the time series in a certain way, namely the red one, which corresponds to probability 10%, has 10% of the points below this red curve. For the green one, which corresponds to 50%, 50% or below, and for the blue one, 90% or below. So, all right, now if I look at the residuals here, the residuals for the 0.5, I mean, you can see that the part which I'm interested, the part I said where it's kind of anomalous, right? It's actually, it's kind of, you can see that I have quite a lot of error. The errors are big enough, and you can see that one of these methods, if I use, say, relative errors, you know, it's going to identify those. I might consider using different tuning some of this of the thresholds, tuning some of the regression quantiles. What is more interesting in this is that I'm basically looking into these errors. These are the residuals. I'm subtracting. In some sense, you can say that these plots here, well, the signal being detrended. So I'm subtracting the values of the points from the actual curve. And now I'm looking for outliers here. I'm looking for outliers, or I can specify a threshold. So you can see if I specify a threshold 1 for this particular case, I should see that these points, you know, at threshold 1 is being specified. If I decrease my threshold, right, I mean, I'm going to have more outliers. Again, if we go here, right, 0.4 is somewhere here. So more outliers were being presented. What is interesting, and one of the things we can do with quantile regression, which you cannot do easily with other methods, is that we can find anomalies using variances. So I can, with quantile regression, because I can put arbitrary number of quantiles like that, first I can do the conditional cumulative distribution functions estimation. At each of these time points, I can actually reconstruct what the signal is like. Say, if I put here 75, right, and if I put, say, 0.3, right, I'm going to have more curves being fitted into this. So, and now, because of the quantiles, I can actually, as I said, I can do this conditional probability distributions. I can make an estimate using this kind of curves. Now, let's go back to the variance anomalies though. The way I have fitted this, and I might increase the number of fitting points. This gives me a way to estimate the variance. If I look into the points between the curve with probability 90% and the one with 10%, I can see that the ones, I can try to find the anomalous variances. This is what this variances is here. So I'm using a Champaign identifier to identify the anomalies. If I use S plus quartile, which is more conservative, you can see that the anomaly is being here, which actually it is anomaly. If we join the plot, we kind of see that this here, it's anomalous. And so I can also do, I mean, I can do some other stuff related to that. Some of these algorithms, they can be helped in some way. Like, for example, if I put only one probability, 0.1, and look into my point probabilities here and use absolute errors. Let me see. Can I convince you that this is going to work? So I might, you know, and use not so many degrees of freedom on number of knots for which the quantile regression is done. I can actually identify these points here as anomalous. So, all right. So again, we might say that's great, but it's how we actually do find estimates for this. Like how do we detect which algorithm, which parameters to use. And this is my last example. I'm just going to, actually, it seems to me that I need to extract this in some way. So, all right. So I have a way to produce random, they're not exactly random time series, but I have a way to produce time series with random outliers in them. So you can see I have a bunch of time series. They come from different temperature data, like say Boston, Chicago, you know, Orlando, and I have put outliers in them, and I know which outliers, which points are outliers. Now, I'm going to select one of those. I'm going to put this quantile regression object, and with my quantile regression object, I'm going to ask myself, fine, I have this algorithm which can detect anomalies using quantile regression. Basically, I'm detrending the signal. I'm looking for the outliers. But what parameters should I choose? So I have made this outer product, Cartesian product of different parameters. You can see I have like 18 parameters. Like, do I have a threshold? What is the threshold? Is it with relative errors? Is it with absolute errors? Which outlier identifier is going to be used? So I have 18 like those. And then I run the algorithm across for this time series. I run this algorithm. I run it with all of these parameters. And then I'm going to be finding what is my success ratio? So how many times my algorithm did actually figure out which points which are marked as outliers, but they're actually outliers. So you can see here I have this true positives, false positive, and etc. What is interesting though, I'm using here receive operating characteristics. I assume everybody is familiar with this to a point. So the terminology which is being used is here. But so here I can see how of these different parameters, different algorithms, how they behave. Obviously, I might say, look, false positive and true positive. I mean, if you look at this, this is not exactly a classification algorithm. The number of points compared, I have like say 2,000, 2,200 points in this data. If we look at the summary here, we actually have like relatively small number of outliers, anomalies, and then we have very large number of points which are not anomalies. So classification is not exactly something you can use, and receive operating characteristic comes from classification workflows. We might decide to use a different formula. So this here is a weighted formula of some of the rock characteristics, and I'm going to run this shiny app, which is going to demonstrate how if I change my, so in this, instead of 1/5, we have this parameter theta, right? So if I change it, then different these algorithms have different behavior. So this is as I said, the main message. You come up with an algorithm. You make a lot of time series with different type of anomalies in them. This is not the only type of anomalies we can consider. We can just to go to the mathematical one. Imagine you have anomalies like this, right? And then we measure the success with different parameters, with different time series, and we want to find out which algorithm with what parameters behaves best. All right, so I think I'm over time, and I didn't have time to discuss structural breaks, but you can find them in the referenced article and videos. Here is, an example of how structural breaks are being identified. And again, this is some time series analysis, financial time series. All right, thank you for your attention, and I'm willing to answer questions.
Thank you so much, Anton. Just proves yet again how strong regression-based techniques are for various applications, and that window overlap method is pretty interesting. With that said, we do have a second presentation, but I did want to open it up for any questions or comments. If anyone would like to ask a question or give a comment, I'll just pause for that, and you can just unmute and please share. Okay, well, if anyone has any subsequent questions for Anton, we can take questions again at the end for both presenters, as well as Anton has, again, put all of this on GitHub, and you can communicate directly with him as he's presented some pretty interesting techniques, which he's clearly spent quite a bit of time on thinking about, and pretty exciting with regards to time series data. So right. With that said,
thank you.
Oh, go ahead, Anton.
No, thank you. Yeah.
Thank you. So next up, we have Matt, and Matt had told me that he'll kind of introduce himself, and well, we all know him, so he'll introduce his topic himself.